All right, clip number 2 for section 3 notes on using chords. We're going to do these 2 examples today that apply the theorems that we talked about in the previous clip. All right, example number 1. Example number 1, we're given a diagram of these 2 circles. Now, I did this on purpose in the notes. I wanted to emphasize that technically you might be given one or the other, and here's what I mean by that. I explicitly write out the geometric language, everything that's also visually expressed here in the diagram. I want to point out that you might get one or the other. In other words, you might just be given a diagram like this, and they're like, okay, now solve for this piece. Or they don't give you the diagram at all, and maybe just some blank circles, and then they give you this information, and then they're so like, okay, now find this piece. So I'll kind of show you what the difference is right now. Okay, so first off, we're explicitly told that circle P is congruent to circle Q. So I've mentioned this a couple times. I'll keep mentioning it throughout the chapter. Anytime they name a circle, they name it after its center. Okay, so circle P, that means P is the center of this circle. Q is the center of this circle. And that matters here because that means that this segment, P to the edge of the circle, is the radius of this circle. Q to L is the radius of this circle. And so the fact that both circles are congruent means that those radii have to be the same measurement, whatever it may be. And that's actually shown here visually with those dash marks. So the double dash here and the double dash here means that those two are congruent to each other. So that's how they show that 2 circles are congruent. So whether you're shown that visually in the diagram or just explicitly told, you might see either or. Okay, next they tell me segment FG is congruent to segment JK. Both of these will end up being chords. FG is the chord here at the bottom of this first circle, circle P. JK is the chord here on the left of circle Q. I did that on purpose again to show you that the chords don't necessarily have to be oriented the same exact way. Okay, it doesn't matter where they are, as long as I know they are congruent to each other, again, as shown by those dash marks right there. Okay, so this is essentially going to be that congruent corresponding chords theorem, that C1. Okay, so I have congruent chords in 2 congruent circles. Based on that theorem, it's going to force both of these arcs, arc FG, to be the same measurement as arc JK, because it's 2 congruent circles with 2 congruent chords. All right, and then they tell me one other piece of information that will come in handy here. They tell me that major arc JLK, so this is a reference to section 2 on arc measurement. Major arc JLK, that's J to L to K, this major arc here. It's actually explicitly drawn as well. They tell me that that's 280 degrees. And that's it. That's all they tell me. Based on that information, my job here is to find the measurement of arc FG. FG is going to be this arc down here. Just to remind us, the measurement of an arc at this point will be in degrees. So I know my answer needs to be in degrees. All right, so here's how I can use that. I know that this arc FG, the one I need to find, it has to be congruent to arc JK. So if I can solve for JK, I can just copy and paste that over here for what I need to solve for. That's why they go through the trouble of all that information here. It's the congruent corresponding chords theorem. Okay, so based on this circle then, they tell me that this major arc is 280 degrees. Hopefully you remember from section 2 that all circles have a total of 360 degrees. I can use that information to figure out what's left over here for this minor arc. If that's 280 for that major arc, I could subtract that from 360 to find out that I have 80 degrees left over for that minor arc. So arc JK is 80 degrees. That's all section 2 stuff right there. Now to apply the theorem that we learned in this section on using chords, the fact that these 2 chords are congruent to each other forces their minor arcs to also be congruent to each other. So if that's 80 degrees, that must also be 80 degrees. So to answer the question, what's the measurement of minor arc FG? 80 degrees, because it had to match this guy, and that's what degree was left over after the 280 was used for the rest of the circle. Done. Okay, as far as what work I would expect to see here, again, you can see that upload onto Google Classroom. It'd be a small subtraction problem to figure out what's left over here for JK. And again, because of that one theorem, that's going to force arc JK to be the same as arc FG. That's how we got to the 80 degrees. Done with that one. All right. Last example for section 3. Scroll this down a bit. Here we're given a different diagram. Surprise, surprise, it's a circle. And again, they do give me some critical information here just in the name of what information they told me, that it is named circle M. Naming a circle identifies the center of that circle. So circle M forces point M right here in the middle to be the center of the circle. And that matters here because that forces this JL segment, this JL chord, to be the diameter of the circle because it goes through the center. So JL, just simply by naming the circle circle M, it forced JL here to be the diameter. If it didn't name circle M, or I didn't know, I'd have to do extra work to show that that had to be a diameter. And a diameter is a very critical piece of a circle, so it's valuable information. Okay, and then they give me some other information here. I have another chord, HK, that's crossing this diameter that I now know it's a diameter. So I get this T shape, X shape, whatever you want to think of it as, in the middle of the circle. Okay, this Xbox logo, if you want to call it that. All right, so in this diagram, I'm asked to find two things. Again, here's just a little bit of tutorial on geometric notation. When they say find HK, this is the length specifically of a segment. If I were to have the bar over it, that would be the geometric object, the segment. When it's just HK without the bar, now it's literally saying how long is that? What is the explicit quantifiable measurement? What's the length of that segment from H over here to K? For this one, this is now in the arc notation that we had in section 2. We see the little arc symbol right there. The M simply means measurement. So again, it's looking for the quantifiable number that will represent this measurement. So in this case, since it's an arc, that's going to be in degrees. This one will be in length, so that might be in like feet or miles or centimeters. This one will be in degrees. All right. So the theorem that's going to be used here is the perpendicular bisector theorem. All right. That theorem basically said this: if in the same circle I have a diameter, and that's the critical first piece of information I need to know here. If I have a diameter, and I definitely do with JL, that intersects some other chord perpendicularly, that forms a right angle. That little box right there, that's critical right here. Makes a right angle, makes that 90-degree intersection. If I get this situation where a diameter intersects a chord inside of a circle at a 90-degree angle, that diameter is chopping that chord in half exactly, and also that arc created by that chord in half exactly. And that gives us all the information that we'll need for these next two pieces. Let me start with part A, because part A is going to be the least amount of work, so to speak. All right. So because of that perpendicular bisector theorem, since this diameter JL is crossing chord HK at a 90-degree angle, it needs to chop it in half. So geometrically speaking, I would say the following. Segment HN has to be congruent or the same measurement as segment NK. That's just chopping in half that chord, HK. All right. That's valuable information because I actually know here in the diagram that NK is 7 units long, whatever units those may be, which is then in turn going to force HN to also be 7 units. So just be careful here with what the question's asking for. It may ask for like, okay, what's HN? What's the other segment? Well, it just has to be a copy and paste version, so that would be 7 units. But here in this problem, it says find all of HK, which is the whole chord. So many of you would just simply take that 7 and multiply it by 2, and that's perfectly accurate. It'd be 14 units long for the whole chord. The longer algebraic way would say like, okay, if that's 7, then this must also be 7, and then I would do HN plus NK is equal to all of HK. That's the segment addition postulate, where I would have 7 units plus 7 units getting to that same 14-unit result. In either case, hopefully you see that because of the fact that that's a diameter intersecting the chord at a 90-degree angle, because of that theorem, these two halves need to be the same measurement, so I can quickly find out what the whole chord is. 14 units. There's part A. All right, part B. It's basically the same question, but now I'm dealing with arc measurement, and it's going to be the same type of process because, again, I have a diameter meeting this chord at a 90-degree angle. It's going to force this situation, this diameter, to be chopping that arc in half. So geometrically speaking, that would mean that arc HJ from H to J needs to be congruent for the arc from J to K. So geometrically speaking, this would have to be true because, again, of that perpendicular bisector theorem. And so this one's a little bit more interesting than part A because here I actually have algebraic phrases. So just to kind of translate this into what this would look like from work, instead of just being given an explicit number, now I would say like, all right, well, whatever HJ is, in this case, 11x, that needs to equal or be equivalent or match the other one, which JK in this case is the 70 plus x. And I end up with this equation. And basically, if I can get to this point where I set up the equation, I can quickly solve for the variable. It's just combine like terms, move stuff away. This should be now something you've done for years, right? So in this case, combining the x's together, I would subtract x from both sides, and I would get 10x here on the left is equal to 70. I would divide by 10, and I would get that x equals 7. All right, very tempting at this point for a student to stop. They're like, hey, I solved for my variable. That's all I ever had to do my entire algebraic life. Just solve for a variable. I am done. The answer is 7. But again, good advice for everyone. Anytime, any class that you think you have answered the question, double check and look back at what the question is asking. So I know that x is 7. Great, congratulations. That is an important piece here. But look back at what the question is asking for. It's asking me for the measurement of arc HK. So it's looking for the degree measurement of this entire top arc. Meaning, in this case, I actually have to take that x value of 7, plug it back into each of these algebraic phrases, and then I just add them together. That's the arc addition postulate right there. So if I plug in 7 right here, 11 times 7 is 77. That forces arc HJ here to be 77 degrees. JK, I already know has to match that. I could confirm it by plugging it in, but it's going to be 77 again. So JK is also 77 degrees. So all of HK is 77 times 2, which would give me 154 degrees. The measurement of arc HK is 154 degrees. Now, it could also have asked me here, like, hey, now what's major arc HLK? Well, having found HJK was 154 degrees, I could subtract that from 360 to find the remainder over here. So there are different ways that you might be tasked with finding something, but they're all kind of tied together there. So that will conclude our section 3 notes on using chords. I'll go ahead and stop the recording there.